We left off last time talking about static electricity and electric charge, and what happened to all our lights? We took them out for those. We left talking about static electricity, static charge, charges, all this stuff, what they could figure out way back when, a couple hundred years ago. No, yeah, over a couple hundred years ago, 250 years ago with electricity. And we came to this dilemma. The dilemma was, okay, you've got a charge. How the heck does it affect this charge over here? Okay? We have this whole action at a distance problem. Okay? And they didn't know how this mechanism worked. Coulomb had come up with his law, right? Coulomb's law is? Yeah.
1, 4, 5,
All right, so there is Coulomb's law. Coulomb's law works great for any pair of charges, but the issue was this, okay, it describes the force between any two, but how does that force happen? Because they're not touching, right? That was a big deal back then. They weren't touching. You know, the not touching thing is not that big a deal for us today because we have magnets, we see how magnets affect each other, and they don't touch each other, right? So we're kind of okay with that mostly, but here's the real dilemma for us, is that if you move this charge from here to here, okay, the force was here, and if you move the charge from here to here, now the force is supposed to be here. And it swings this way. The question is does that happen instantaneously? How does the other charge know? And when does it know that the other one has been moved? Okay? Like for instance, if I move from here to here, when do you know?
As you're moving.
Do you know instantaneously that I'm moving? Really?
We don't know where you're moving to, we just know you're moving.
If we're slow-minded, we can't.
You have a receptor in your brain that
That's right, you have a receptor in your brain. Alright.
So if we see you moving.
Now, as far as if you were timing it, you would say it's instantaneous. Now, there's a biological delay, right?
Right.
For when it has to...
Speed of light to our eyes.
Okay, first of all, there's a physics delay. The physics delay is the speed of light to your eyes, because when I move from here to here, that information is transmitted to you at the speed of light.
Yes.
Okay? And then your eyes have to pick it up, and your neurons have to send it to your brain has to interpret it, right? So there's a couple of delays. One is a physics delay, one's a biological delay. The biological delay, by the way, is also a physics delay of all that electric circuitry going through, electrochemical circuitry going through your brain. So it's really physics, chemistry, and biology all combined on why you don't get that information and understand it instantaneously, right? Okay, now we're not talking about chemistry and biology here. We're just talking about when does this one know? Does it know instantaneously? That's the real issue that they had problems with, okay? All right, so let's go back to... By the way, Newton and Coulomb, Coulomb said it happened instantaneously. Newton would have said the same thing. In fact, I don't know if Newton wasn't around at this time, I don't think. But according to Newton's ideas, it would happen instantaneously. All right? Now, along comes Michael Faraday. Did I tell you the story of Michael Faraday? Poor, extra poor Michael Faraday? Okay, Michael Faraday was dirt poor. Okay, he was born in 1791. He died in 1867. Okay.
76.
I have 76 as well.
Oh, really?
Yeah.
Bummer. That's wrong. Hey, whatever. Just rearrange it. He died in 7,681. This guy had almost no education, and so he had to work his way through, well, he had to have a job, right? And so, but as luck would have it, he was very bright, and so he got a job at a bookbinder, and he educated himself by reading all these books, because back then books were like gold. They were very expensive. and if you had books, you were rich, okay? Took a lot of money to print a book, bind the book, buy a book. And then if your book binding broke, like a lot of your books have done, your college books will do that because they make them so that they destroy themselves after about a semester, okay? That's all they're made to last, okay? Yeah, self-destruct. The pages will be fine usually, but the binding will usually break off the back.
But then Andy can burn them for heat.
That's right. Or maybe weave some boots out of them.
Oh my god.
I can't rebind a book though.
Excellent.
Yeah.
So you, like Michael Faraday, can rebind a book, and he would read these things as they would come in, and his employer would allow him to read them as he was rebinding them, which was very nice of him. And then one day, Encyclopedia Britannica comes in, and he reads this section on electricity and magnetism, okay? And that started him on, he kind of found his place, what he was really great at. It really intrigued him. And so he learned and learned. He found a way to get through college and to get himself educated. But since his learning started later in life, he always had trouble with math. Math was difficult for him. I say difficult. His math was probably greater than all of ours combined. But it was difficult for where his brain was taking him. His math wasn't up to snuff, okay? And so he had to come up a lot of times with ingenious ways of viewing problems. And his ingenious ways of viewing problems were a lot of times visual, graphical, things like that. Somewhat like Stephen Hawking has done, is that since he can't really do much, he kind of visualizes the problems in his brain. So anyway, so he came up with these pictorial methods to describe physics, and probably the most important one he came up with was the idea of a field. He said, look, okay, this charge does not affect this charge in any way. It doesn't do anything to that charge. What this first charge does is it affects space. It literally changes the space around itself and makes the space different. Now we can't visualize what that is directly because our eyes can't see it, okay? But there are ways to kind of visualize some of these things. Have you ever seen a magnetic field visualizer? Sometimes you'll see those things, it'll be like a fluid with a bunch of little metal filings in it.
Oh, yeah.
And you put a magnet in there, and then the metal filings will line up along the magnetic field, like on a piece of paper. Do you have one up here?
I just stuck
We
my
did that
hand in
as
it
well.
because it was cool.
Sophomore year.
Yeah.
Oh yeah, right here. Okay?
Take it out. It comes out.
Okay, here's one right here. Now these are just metal filings. That's a cow magnet in there, isn't it? Okay? All right, so you
can
have...
take the other thing out.
Oh. All right,
Isn't
so
actually there.
here's a cow magnet. You know what a cow magnet is?
Yes, they
Yeah, they say open up cow, and they feed this to a cow.
So that it takes all the metal and
Yeah,
stuff.
because cows aren't the brightest animals, and so they'll just graze and eat whatever's on the ground. If they eat something metallic that's sharp, like a nail, they'll eat it. Okay, if it's just sitting there, they'll eat it. And as it goes into their stomach, remember they have multiple stomachs? Burp it back up, chew the food, swallow it. It hurts them back and forth multiple times, and so they capture these things in their first stomach with a magnet. Yeah. All right, so you can shake this thing up and you can get a view of the magnetic field. All right? I'm going to keep it in this so this doesn't fall out. Actually, here, just be careful. It'll fall out both sides, all right? So I'm going to start it right here. So you can shake that around. And so those filings will line up along the magnetic field. You've done that sometimes in like elementary or middle school. We have iron filings on a sheet of paper and a magnet underneath. Okay, same thing. Electric fields are a little bit harder to visualize like that. But so we have this idea of the field, something we can't see, but we can represent with a drawing. So he said, here's the deal. This object produces an electric field. It's the changing in space. Space changes around itself. And so what happens is this charge does not react directly to this charge over here. What happens is charge number 1, plus charge, changes space, makes an electric field, and this charge is influenced by the field itself, not by the original charge. Does that make sense? Okay. kind of like an asteroid hits the Atlantic Ocean. New York, Washington D.C., Miami, they're all destroyed, but not by the asteroid, but by the wave that was produced, right? Now, does the asteroid instantaneously destroy those cities? No, there's a time delay. And that's the thing that Faraday said as well, is that what happens is if you move this charge, the field will propagate outward at a rate. Okay? So this charge over here doesn't feel the change in space instantaneously, because it takes a while for the change in space to propagate outward. Just like if you drop a rock in the Atlantic Ocean, Miami doesn't feel it instantaneously. Okay? There's a delay time.
Comes in a hurricane.
Not a hurricane. Tsunami. Alright, so electric, magnetic, and gravitational objects influence space itself, and other objects react to the space, not to the originator, not directly, to the originator of the changed space. Okay? So this is the mechanism for force at a distance. And that propagates outward, this alteration in space propagates outward at a given rate. Okay? At a finite speed. Okay, at first his idea was viewed as a pictorial gimmick. Okay? But by the end of his lifetime, at the very end of his lifetime, in 1865, James Maxwell had taken these ideas from Faraday and from Ampere and from Gauss, and taken those ideas and put them all together in one big picture. And the central feature of that picture was the idea of a field. Okay? Electric fields and magnetic fields. And what he actually was able to predict just from those, actually they're called Maxwell's four equations. Maxwell didn't create any of those four equations. He just brought them all together. He modified one of them. But he was kind of the project engineer that brought all of it together, put it all together in one coherent form, and from that was able to come up with the idea of an electromagnetic wave. And if I remember correctly, you remember this symbol and you remember this symbol, right? Epsilon naught and mu naught. Well, this is essentially, you know how we have this in gravitation? Universal gravitation constant. I wish they had called these this. This is the universal electric constant. This is the universal magnetic constant. But they call them like the permittivity and permeability of free space. Okay? Whatever. They're the electric and magnetic constants. The basic constants. Alright? And if I remember correctly, he predicted that there would be this thing called an electromagnetic wave, and the speed of the wave would be, actually the speed of the wave, I should do this first. If I remember correctly, is this.
Oh, that's cool.
I have to check that. I'm doing that from memory. I think that's correct. So the speed of the wave depended only on those two constants. And if you take those two constants and put them in there and figure that out, I believe that turns out to be 3E8.
That'd be beautiful.
And so he said, you know what? I think that's the speed of light. So light must be an electromagnetic wave. Somebody check that for me.
People are way too smart.
I know. How he figured that out is crazy. All right. And by the way, Maxwell's four equations turned out to be the only four equations that were not proven to be wrong by Einstein's ideas of relativity. Okay, remember relativity showed us that F equals ma, and a lot of these things aren't exactly right, that they're great approximations as long as we're not moving too fast, or as long as there's not too much mass around, gravitational field. But Maxwell's laws turned out to be perfect. Come out? Is it about right? Yes.
It's giving me issues.
Uh-oh. We have confirmation over here that that's 3E8.
That's really cool.
All right, so here's the field model, everybody.
Makes me happy.
Number one, the field, the source charge alters the space around itself and creates an electric field, which we call an E field. Okay? Number two, a separate charge in the electric field experiences the force exerted by the field. Okay?
Wait, what?
One charge causes an electric field. This charge experiences the effect of the field. Okay? So this second charge, if it's not there, the field is still there. Okay? So the first charge creates the field. The second charge experiences the effect of the field. So there's already something in space for that second charge to feel. Okay? Does that make sense?
Yeah, but which one's the first, which one's the second?
Ah, yes. It depends on the way you describe it. Okay? Great question. The question is, well, how do you know which one's the first charge and which one's the second charge? It depends on whichever one you're thinking about. So, like here we go. So I'm going to call this my first charge. My first charge creates an electric field. So then I'm going to call that charge number 1. And then I put another charge out here. So this space has been modified. I'm going to put another charge out here. I'm going to do a plus charge. Okay, this is charge number 2. How will I know when I place charge number 2 out there if there's an electric field?
It'll be repelled.
Yeah, it will experience a force, right? And so the original way to figure out what an electric field is the definition of an electric field is, well, you place the object out there, if there's an electric force on it, and then you just divide by the size of this charge. So a lot of times this is called the test charge. If I wanted to find out if there's an electric field in this room, I would take a small charge and I'd place it in the room, and I'd see if there's a force on it. I'd take that force, divide by the size of the test charge, so that the test charge size wouldn't matter. Okay? And then I find out what the electric field is. Note the units. The units are newtons per coulomb. Okay? Those are our units. And it's a vector. These are vector ideas. Now, so what do you use for your test charge?
I'm going to use.
Number 1, it has to be small. Why does it have to be small? Yeah, so it doesn't make a large enough electric field of its own to influence space much, right? So how small is small? Well, as small as you can get it, the better. But, you know, as long as it's 100 or 1,000 times smaller, you're going to be in pretty good shape, okay, than what the other charge is, in a sense. All right, so we got that. Second thing is what sign is the charge? Because we got a plus or a minus.
Does it matter?
Call it.
It doesn't matter, except if you put a plus charge out here, you get a force in one direction. But if I put a minus charge out here, I get a force in the opposite direction, right? Either attract or repel. So by definition, they've decided that the test charge is always positive. Okay, so that sets up the direction of our electric field. Okay, they're just setting up a convention. Okay, why do we read from left to right? Because somebody's...
It would have been easier to do the other way around, but no.
Or top to bottom, or right to left.
Yeah.
What Hebrew is right to left, isn't it?
Yeah.
Some Chinese, some of that's top to bottom.
Wouldn't it be more convenient if we read like this?
We read from top to bottom.
Yeah. It would
Actually,
be,
you know what? It would be really easy if we started and read like this. You're correct. It would be faster if
That'd
we
be
read that.
awesome.
That's how I count my words in my essays.
We should. I think we should just read like this.
Just continue.
Like a CD.
Spin the
Yeah.
book.
You set the paper down. The paper's round.
and you spin it.
And it spins. And you read.
Invent it.
Invent it. All right, then. All right, children, take out your circular pieces of paper. Does anybody know that reference?
What? I missed it.
It's an old reference from The Simpsons.
Wait, say what?
All right, children, take out your circular pieces of paper.
Wow, that did not.
It's The Simpsons when Homer gets hired by this arch villain to run his nuclear power plant, and they go to someplace in Colorado, and it's all magical and perfect, and they have these advanced schools, and Lisa's in heaven, and Bart's in the remedial class, and they all have circular pieces of paper because they took away the pressure of where to start on the page.
Wow.
Oh, no, no, too much pressure.
Where do you start? Anywhere you want. There's no edge. There's no top or bottom.
But do you start in the middle or at the end?
Hey, I don't know.
Oh, yeah.
You should just have a Mobius strip then. You can start anywhere. It's all the same.
Then you run it.
Yeah. That's what our book should be like, on a Mobius strip. That's right. All right, everybody. Now,
You rip off.
if, yes, if this is a point charge, okay, like if this is just two charges, what does this electric field turn out to be like? Well, the electric force between these two is 1 over 4 pi epsilon naught Q1 Q2 over R squared. So if you plug that in, the electric field for a point charge is going to be 1 over 4 pi epsilon naught Q over R squared. Now I'm going to put capital Q to remind you that that's the charge that is creating the electric field, not the test charge that is measuring the electric field. Okay? So this is our electric field in general. This is if it's a point charge. It's very important you write down point charge. Okay? Because we're not going to have point charges all the time.
That's 1 over 4 pi epsilon naught?
That's correct.
It looks like whatever full pi sheet. Yeah.
Whatever.
It looks like a cave.
Now, also everybody, if you know the electric field and the charge, remember it's easy to find the electric force because a lot of times we're wanting to do F equals MA. And if so, then we just rearrange this. This is EQ. So if you know the electric field and the charge in the electric field, you can find the force on it. And the direction of the force is for a positive charge. Okay? So if you have a negative charge in here, then the force will be in the opposite direction. Okay? All right, so what does an electric field look like? You've seen these many times already. So please draw the electric field, what it looks like around this object, and then separately draw it around this object. And I'd like for the second object, this one, to be twice as big as the first one. Okay, two separate diagrams. How are you going to draw those electric fields?
Didn't you say there was like a minimum amount of arrows that you had to put?
Well, you need to demonstrate that it goes off in all directions. So probably, if you have a point charge, a minimum of 3 at least to show that it goes off in all
Can we just
directions.
say in all directions?
Yeah, let me put it this way. If you draw your electric field like this, I guarantee they won't give you full credit.
Is that the answer?
No.
Why would they not
Does it go in that direction?
That's not what you drawing
Okay.
fields.
That's probably at least the minimum. A lot of you will draw 4. Okay. Here's 6.
I'm being
Okay.
over
3,
here.
4, 5, 6, whatever. As long as they're pointing away. Why is the electric field away?
Is it a track?
Because if I put a test charge here, it would be forced away. So the electric field is away. Does that make sense? The electric field's set up as if you have a positive charge out there.
Looks like a set.
Okay, what will this one look like based on what I've drawn here?
12 going in?
Yeah, but there will be 12, right? 1, 2, 3, 4, 5, 6, 7, 8,
They're not just
9,
longer?
10, 11, and 12.
So, why,
They're not just long.
You're not drawing for.
Now, here's the deal. There were 2 options, and you could draw, to designate a stronger electric field, you can either draw them longer or more of them. They decided that drawing more of them was more appropriate, that it was an easier way to do it, okay? So, here you go. Wherever the electric field lines are closer together, you have a stronger electric field. Wherever they're spread farther apart, out here, see they're spread farther apart, okay? It's a weaker electric field. So you can see that more lines packed closer together. The electric field here is stronger than the electric field here, right?
Beans are attacking.
That's right, human beings. All right, so if I have an electric field drawn like this,
Huh.
okay, there's my electric
Oh,
field.
it's stronger right there in the middle.
Yeah, we have the strongest electric field right here. It's stronger there. And it would be weaker out over here. Okay?
That's pretty good.
Now, next thing is, what about right here, this spot? If I put a positive charge right here, which direction will it experience a force? First of all, will it experience a force?
Up.
Yes.
No,
Which
you
way?
Just follow that line.
You're right.
It'll follow the line, so it'll look like this? Okay, because it has to be a straight line, right? So it's got to be a vector line, which would be straight tangent to the line. Okay, but what if they gave you one right here? What if they gave you a plus charge right here? Which way would you say the force is?
More than one direction.
More than one direction.
To the average tangent.
Average tangent, so you would draw something like that. Okay, but then they're being wise Alex, thank you, smart Alex. Got myself. Which way's the force on that one?
Down. It's the average tangent down that way. Because it's negative.
Negative charge, instead of being tangent in kind of this direction, is tangent in this direction. Opposite. Okay? So there you go. All right. Okay, will you please draw what the electric field looks like if you have a plus and a minus, like that? And what will the electric field look like if you had a minus and a minus? What would it look like for those two situations? So here's the deal, everybody. If you know these two, you should get by with being able to draw most electric field diagrams if you get the concept of these two. Okay, just put a little point charge right here. That's a positive charge. Which way does it experience an electric field?
To the negative.
Okay. Toward the negative, because it's repelled from this one and attracted to this one, so there's going to be an electric field that way. Okay? What about if I put a point charge right there? Which way will it experience a force from that one?
And down to the left.
This way, right? And which way will it experience force from this one? Down and to the right. And so the combined nature of those two is still downward, right? Okay, but how is that downward compared to that downward?
It's curving downward.
Are they the same strength?
No.
This one ought to be bigger, right? Okay, and then over here it's going to still be downward, but it's going to get less, right? Okay, now, so we have an idea that you're going to have a line from here to here, right? They always originate on plus and end on minus. Always originate on plus, always end on minus. Okay? So wait a minute, so this one's going to point down, but what about when I'm right here? Which way is it going to be there? Okay, which way is it going to experience a force from that one?
That way.
To the left. Which way is it going to experience a force from this one?
Southeast.
Southeast. Will it be the same size as this one?
No.
No. Okay, so it's going to be less. So you're going to end up with something this direction, right? So you're going to have something out this direction. Okay, so do you see it's going to bend this way, and then if I put one over here, which way is it going to be?
Bending.
Down this way, right? So we have things that go like this.
Stand right at the
That works.
So it looks like that. A lot of times in your books they're faced this way, horizontal, so I did it vertical just to make you see it a different way. Okay, what's this one going to look like?
I don't remember. That's everything out.
It goes
What's
away
the electric
and-
field look like right here?
There. Nothing. It's just there.
Nothingness, right? Okay, so you got nothing, a dead spot right here. So, okay, so what about right here?
what?
away.
Okay, it's going to be away, toward, and toward, which would be down, right? Okay, so this one's going to be down. So, and over here it's going to be up, right? Okay, so what about over here? It's going to be this way and that way, but so it's going to be somewhere like this, right? This one's a little bit harder. So what if I put one right here?
This is really difficult how you're doing that with the points and all that.
You have a better way to do it?
No. Well, I don't
No,
know.
no, I didn't mean that like, I didn't mean it that way. No, do you have a better suggestion? Because I'm open for suggestions.
No, just like we didn't. Well, I didn't learn it like that. We just kind of drew arrows on it. We didn't do the
Now,
point charge thing. So this.
Some
is kinda
people will do
confusing.
this, where they'll just draw them like this. But I have trouble personally seeing how these overlap. I mean, you could say, well, these two add to be down, and these two add to be. I don't know, you can do it that way if you want. But what this turns out to look like is it comes down and turns, and there is a dead zone in the middle.
That's
And they turn in this way.
It's a 3G dead zone.
Okay? Looks like that.
You need someone to point out the map.
And literally the way they map these out is they just make a grid of little point charges, and they see which direction the little arrows point, and then they line them up and connect them. Okay, a couple of things. Number one is that the arrows are always tangent to the force. The force will either be with or against tangent, whether it's plus or minus. The electric field lines never, ever, ever cross each other. Okay? They're like streamlines, if you remember from fluids last year. They never cross each other. All right? Where they are more compact, the electric field is stronger. Where they are spread farther apart, the electric field is weaker. Okay?
Mr. Boone, on that axis, like, is it 0 all across there? Or-
0. Oh, good question. It actually is not 0 all across here. Like there has been a question on the AP exam like this before. And they'll have like A, B, C, D, and E.
Right,
And
C
they'll
is-
say, okay, where is the electric field the least?
C.
Okay, it'll be absolutely 0 here. Right here it won't be 0 because there will be more of an electric field to the left from this one than there is to the right from this one. Okay, so what actually happens is right here, it will actually have a line like this and a line like this with a dead spot in the middle.
So, but if those are positive charges, right, and I put a positive charge like to the left of 0, will it oscillate?
Yes, so like for instance, if I put a negative charge right here in the middle, it will stay put. If I put a negative charge here, it will be pushed to the left, and then it will oscillate back and forth like this.
Until it settles down.
And actually, it's one way they can make an oscillator,
Oh,
it's like that.
that's ugly.
Okay. So you can have like a containment field if you like. Just put a bunch of pluses like this. Actually, they wouldn't make it square; they'd make it round. And if you put a plus charge, a plus charge inside of here, it would oscillate around and move around like this, but it would be stuck inside.
So sad.
It's a little proton prism.
Oh, this is really sad.
If you were in a proton prism,
Okay.
given a suit.
So now it's time for us to calculate some fields. So you got your brains going?
Funny. Mr. Boone, we have an idea for
A prison.
future prisons. You just wear a charged suit, and like you wouldn't have to build walls. Just have like electric fields.
Oh my god, like, we can leave.
Well, like they'd be pushed back
That
if
was
they
so
ran.
depressing.
Well, you'd get to see.
Kids would take their clothes
Other
off
people.
to leave. Yeah, there'd be a lot of
Ready? Please calculate the electric field at the dead center of that triangle, equilateral triangle, please.
No.
Yes. Now, this will require this mystical science or mystical math we call geometry.
Oh no.
Okay?
I don't do that.
Now, if you're doing one of these problems, first of all, do we have point charges? Yes. Can we then use this to calculate the electric field?
No. Yes.
Yes. How many times will we need to use this?
None.
Andy?
One,
You said there was
2,
another
3
one that we
times.
used.
0.
3 times, right?
Yes.
Because we will have an electric field here, a change in space right here due to 1, 2, 3 different charges, right? Okay, now, use your brain.
Okay.
Use your brain, use your brain, use your
Mostly
brain.
down.
Every one of these, everybody, you need to start using your brain as far as thinking about these things to make your life simpler.
Wait,
I want to make my life simple. So, how can I make my life simple when I solve this?
are we drawing? We're solving yourself.
What's that?
Those charges are the same.
Okay, these two charges are the same, so I can calculate the electric field twice. That's my first thing. Okay, so the electric field from the 2 nanocoulomb will be what? It'll be 1 over 4 pi epsilon naught Q over R squared. Okay? Q, there we go. And then I'm going to figure out the electric field from the 4 nanocoulomb, 1 over 4 pi epsilon naught Q over R squared. And then I'm going to use this number twice. I'm going to use that number once. Okay, before I can get going on this, anything I need to do before I can just plug numbers in?
Figure out the radius.
I got to figure out the stinking radius. Okay, everybody. Geometry. Let's draw an equilateral triangle.
Okay.
Look at that, an equilateral triangle. 10 centimeters. Uh-oh, danger, danger, Will Robinson. Stranger danger.
It's gonna be pointing.
10 centimeters. Is that okay?
No.
No.
No! It's not okay because this constant has units of meters in it, has units of coulombs in it. So that's got to be in meters. We're going to change that. That's 0.1 of a meter right there. Okay, how am I going to find out the distance from here to the center?
Well, you could
Is
make
it?
a right triangle. And then, like,
Yeah, and then do
yeah.
Ooh, now, hang on, everybody.
That's not a
The
straight
mystical
line.
geometry.
And then just divide the other one by 2.
Thank you.
Okay, tell me, because a lot of you are saying, well, wait a minute, isn't this dot halfway between the top and the bottom? Is it really?
Not necessarily.
Not necessarily. Because, see, this distance here and this distance here are not necessarily the same, are they?
Can we just say that it's halfway?
If there's
You
an
can
equation-
say it, but I will say your answer is wrong.
What if we?
There's an equation to find the.
If it's in the middle. Yeah, if we assume that it's halfway, you know, you tell us to like make it. Those are like electrical.
You don't know the equation for the apostrophe thingy? Or...
Okay, let me exaggerate just a bit. What if I had a triangle like this?
Yeah, but that one's not 10 centimeters on each
That's
side.
an equilateral.
on the same triangle.
Do you know for sure the center of the triangle
No.
is the center of this line?
Oh, I see.
Yes.
Yeah.
Doesn't it have to be? It's an equilateral. You said it's in the middle.
If it's an equilateral,
In
it
the
should
middle
be.
of a triangle, not in the middle of a line.
It's an equilateral, right?
It has to be in the middle if it's an equilateral one.
It's equilateral.
You have to draw a 3 line, and I get it in the center of the other one.
Okay.
You're all jerk. Okay, look. Center of this line is right here. Center of this line is right here.
Obviously, you didn't
Center
draw
of
a
this line
triangle
is
there.
right here.
That looks halfway to me.
That looks pretty halfway to me.
You guys are a bunch of knuckleheads. That's not halfway.
I say we draw a triangle right.
There's an equation for a problem.
You can do that approximation thing they do in engineering.
Assuming that it's halfway.
Assuming it's, our triangle is a sphere, it's halfway.
Where's our?
No, it's not halfway.
Fine. Jerk. I'm talking geometry.
In fact, you can prove it's not halfway by drawing your equilateral triangle
Yeah.
inside of the
Let's
circle.
not get on.
No.
That's the center of the circle.
Circle looks falsely drawn.
What? It's a
No. Cheater, cheater,
Mr. Gray, the circle
circle.
I call foul.
I call you all losers, and I say it's not in the center.
Okay. Tell us more about this.
Okay, mystical math time. Mystical math time. Our radius is from here to here, right?
Yes. I believe you.
You believe me?
And then the radius. That's the same, right?
Yeah.
There's an apostrophe there.
You have to take one of the legs, measure the leg, and that's the radius of the circle.
You're going.
Yeah.
I'm not going insane.
No, I know how to do it. No, you're Mr. Bruin. Mr. Bruin.
Here's your radius.
Mr. Bruin. Don't
Yes.
you have to take the radius of?
Oh,
No,
I
you
get it
have to take
now.
the length of the leg, and then you have to put the entire length down the center from the top down to the bottom. Like all the way, like past the bottom. You know what I'm talking about?
Half
Yeah,
the
like all the
bottom?
way through, and then you measure.
Mr. Bruin, I believe you.
Oh, I see what you're saying. You're gonna draw another one here.
No. Okay. Do you want me to go up there?
Okay.
Hey, Mr. Barrett, I believe you about the halfway thing.
You should, because I'm right.
So like, you would measure this because you know when you draw a circle, these 2 points, oh, they might not exactly be.
This is a secant
No,
line for your
that's a
circle.
secant.
Yeah.
Oh, I was gonna say
Just
draw a
signs.
line and then measure.
Okay, everybody, I'll give you a hint. You know more than just 0.1 meter. It's an equilateral triangle. So that's 60. That makes this 30. Right?
That's always really funny.
Does that help?
No.
Potentially.
Yeah, it does.
Now, some of you don't remember your law of sines and cosines.
That was 4 years ago.
Who remembers that stuff?
If you don't remember your law of sines and cosines, because this right here, what's that angle? 120. If you don't remember your law of sines and cosines, well then at least remember that you can create.
That law of sines is really easy.
Law of sines is a piece of cake.
So
But
if it's sine
we
A
can use
over
it.
B over A, sine B over C.
how about this triangle? That's a right triangle. You gotta love right triangle.
And it's halfway, so it's 0.05
That's
meters.
30. That's 60. Whoa, 30, 60, 90.
And the leg is halfway, but we already know that one.
So we know this one right here. This is 0.05. If that's 0.05, what's that one?
Well, we have to
What's
do
R?
cool math.
You have to do cool math. I believe you better begin your cool math because we got a lot to do. Keep going. Now you could use probably the easiest thing for you to do because this is going to be this. This is our x times the square root of 3 number, right? What you could just do is you could just do cosine, right? Cosine of 30 equals 0.05 over r. So r equals 0.05 over cosine of 30. So what's r?
5.
What is it?
0.057.
0.057? 0577? Okay. Let me see if that's correct. I get 0.0577 meters. Very nice.
I'm so proud.
Now, everybody,
Yes.
they can legitimately ask that question on the AP exam.
Now, which radius do you use? Because they're different.
Okay, now here's the deal. What do we want to find? We want to find the electric field right there in the center of the triangle. And so that's our radius to this spot. There's our radius to that spot. There's our radius to that spot. So that's the radius we use in here. Okay? All right, to move ourselves along because we're taking way too much time. We got a lot harder things to cover. This side of the room. Calculate the top 2 nanocoulomb electric field. This side of the room, calculate our 4 nanocoulomb number.
Do we add them all up together? Is it like superposition?
Okay, we add them together, but do we add them with algebra or do we add them with trig?
Algebra.
Is it a vector or a scalar?
Vector.
So we use trig, right?
But ours is only one direction.
4 nano.
And what are units?
Newtons.
Okay, now, does anybody see how we could have made this our lives even simpler?
It's twice that.
Yeah, do y'all see that this number is twice as big as that number? So this number has to be twice as big as that number. So all you really had to do is calculate this number and double it to give you that one, right? Okay, you need to look for these things to make your life simpler. You need to look for symmetry.
I didn't get
Okay.
5,000. What?
It is 5,400
How?
because it's 9E9, and then what do we have? 2E negative 9, and then so that cancels
Isn't
that
that
one.
negative?
And then you divide by 0.0577 squared.
Oh, I forgot squared.
Yeah, don't forget to square that. I know I've said this story many times already, but I took an entire test in college where I I calculate kinetic energy with 1/2 mv to the mv squared. I showed my professor. I said, oh, this is what I did. He said, well, you won't do that next time, will you? It's exactly right. I didn't do it next time. So,
Just the time.
yeah, just the time after that. So you do something, do a bonehead move, and you'll pay for it. All right, so here we go. Now, everybody, remember, some of you are putting positives and negatives on these things. Like, technically that's positive, and technically that's negative. But the deal is what does positive and negative mean again?
Direction.
Does it mean x, y direction?
No.
No. It means radial direction, right? So this tells us nothing in terms of our x, y direction. So I want you to draw right here on this dot, I want you to draw what the electric field, the 3 electric field vectors look like on that dot. And I want you to mark angles. And I want you to draw them to scale.
Oh wait, we're only.
No, it's not that bad.
It's not that bad.
I think I'm done, man.
Oh. Wait, now what are we doing?
I'm not sure what we're doing. What are we doing?
I didn't
How many electric fields are there at this spot?
3.
There are 3 components, right?
Yes.
I want you to draw those 3 vector components right here. Those 3 electric field lines, or vectors, that are going to add up to give us our net electric field. It's the same thing as drawing a free body diagram, right? I have 3 forces, not 3 forces, I have 3 electric fields this time, right? Okay, you should have 3, and when you draw it, you should see the symmetry. Now, with a little practice, you're going to see the symmetry without having to draw this. And you're going to know immediately what you need to do. But you should have one this way and one this way, both 10/800. And you should have one upward, which is a mere 5/400. Okay, right? And by the way, I asked you to draw angles. There should be a 30-degree angle here, and there should be a 30-degree angle here, or you could have marked these as 60 and 60, I don't care. As long as you mark an angle, so we know which way they're pointed.
Yay.
We assume the one up is straight up. Okay, so here's the deal. I'm going to add those 3. When I add those 3, I can't add those with algebra. I got to use geometry, right? So it's vectors, or trig. Trig and geometry. So when I add those, I'm going to use my brain. What is my answer going to look like?
It's very up.
Yeah, it's very up and very little sideways. As in no sideways at all. As in 0. So my answer is going to be this. So, to make life simple, think about what's the simplest way for me to find that from this.
7,400
I've got a part right here that's 5,400
plus
plus
2
2
times 10,800 sine 30.
Got it? That's one way to do it. If you use the 60 here, some of you would use the the cosine of 60, right? So all you have to do is you have this one, and you have to add it to the vertical component of these 2. You have to calculate it once and double it, right? That's all you got to do. Now, it could take you literally a half hour to work this problem.
Yes.
But you ought to be able to crank this problem out in 5 minutes.
Okay.
You're going to need to. All right? By the way, the answer is 16,200, roughly. Newtons per coulomb in the positive y direction, or in the j direction, right? Okay. Now, we are going to have lots more of these kind. We're going to do several more of these, and we're going to find out a way that we can check some of the answers. Okay? But when we go through here, important thing to look at is symmetry. You're going to find out that symmetry is exceedingly important. And in this section of physics that keeping track of, is there going to be only y direction, is there only going to be x direction, which parts cancel out, that sorts of thing is going to really help you out, okay? So when you're calculating an E field, we have 4 common shapes that we calculate an E field for, okay? Four common geometries, okay? Our first one is a point charge. A point charge are multiple point charges, okay? That's what we just did. Where all we do is we apply this once or multiple times and then use trig and geometry to figure out what the electric field is going to be like, okay? It's a zero-dimensional problem. A point charge has no dimension. All right, and then we have a one-dimensional problem, a 1D problem, a line of charge. Okay, so we have a charge all in a line. Now, maybe like a wire, but all of it really is only one dimension. Okay, then we have 2D. A plane of charge. So we have a flat object that's charged up. Okay? Like you have in a parallel plate capacitor. All right? And then we have a 3D object. Like a sphere. And the one we'll deal with is a sphere. We will leave things that are beyond spherical to your college classes. Okay? In fact, your first year of college, this is your first year of physics in college, that's as far as you'll go, spherical. Because once you get past spherical, if you add some other weird shape, then the math becomes prohibitive. All right? And mostly what you will do is we'll show you, you'll start it in here, is you'll turn, like if you have some odd shape, like say it's square like this, and then it's like this, and then whatever shape it is, okay? And you want to find out the electric field right here. What you'll do, technically, is you'll do this for every charge on here. Yeah. Which requires calculus and a computer. Okay? Cool. Which requires calculus and a computer. Because what we'll be doing is we'll be applying this idea to all of these. Okay? So like for instance, when we want to find the electric field right here, we'll find the electric field because of this one, because of this one, and 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 this one. And the radius is changing as you move through space, right? So calculus will be involved, okay? But we'll find out that a lot of these, the calculus solution will simplify down into something that's reasonable. Now there will be some that will be unreasonable, and we'll set those up. But the ones that are reasonable we'll solve, okay? All right, so number one is you need to identify what geometry you have. Is it just a simple point charge or a bunch of individual point charges? Then we just do this over and over again for each charge. If we have a line of charge or a plane of charge or a sphere of charge, we'll talk about those next, okay? We'll go through them one by one, all right? The second thing we'll do is that we will sum up all the electric fields for each individual charge. And then when we get our answer, we're going to look at the limiting conditions, like when you're really close to the object or when you're really far away from the object, to see if it matches up with what we would expect. Okay, like for instance, we had a charge, we had a plus charge here and a plus charge here, and we had a minus charge here, right? Okay, and we found out what the electric field was like right there. Okay? Now, if you're a long way away, say if you're in the back of the room, okay, and there's these three charges, okay, and this one was what? This one was 2 nanocoulomb, this was 4 nanocoulomb, this was 4 nanocoulomb. If you're far away, does the distance between these make much difference?
Nope.
No.
Because you're really far away, right? So what do you see, or what do you feel at the back of the room?
The strength of them.
This is all like one blob of charges, right? And what would you experience from that blob? How much charge does it look like to you when you're really far away?
+6.
It looks like a -2 and 2 + 4 is, so the whole thing together looks like a -6 nanocoulomb.
-6.
Oh, sorry, positive 6 nanocoulombs. So when we move far away from the object, it should end up, the size of the object should not make any difference, and it should just look like it just has +6 nanocoulombs. All right? So we'll look at the limiting conditions and make sure that that's what they look like when we're done. It'll give us an idea of what we've done is correct or not. Okay? All right, so we got those 4 different geometries. So we're going to start with the individual discrete point charges first. All right, so here we go. Here's our next one. And remember, think symmetry. At all times, before you start anything, think symmetry. D, D, here's my point P. All right? I have 3 charges. The charges are all just Q, plus Q each one. Okay, so they're all plus Q. Q, Q, Q. There's my point P where I want to figure out the electric field. All right? Now before you begin, which way is the electric field going to point?
To the right.
Okay, because what we're going to end up with is a component this way from this one. We're going to end up with a component this way and a component this way. Now these two will be the same, right? They're a little bit smaller than that one because they're a little farther away. And then we'll add all 3 of those up to give us our total, right? So before we begin, let's think about it for a second. How are we going to add those up? If we're going to find out our total electric field, what's it going to look like? It's only going to be in the x direction, right?
Yes.
So what's the x part of this one going to look like?
The whole.
It's going to look like the whole thing. It's going to be 1 over 4 pi epsilon naught q over x squared. Thank you. Plus, what's the electric field component from this one going to be like?
It's gonna be
Okay, we're going to need to do a little bit of work beforehand maybe, right? So first of all, the electric field is going to be 1 over 4 pi epsilon naught q over r squared. But the question is, that's this, right? But what's our r? Very good. It's going to be x squared plus d squared square root. Or when I plug it in, it's going to be 1 over 4 pi epsilon naught q over x squared plus d squared because the square root goes away, right? And we'll need that twice. But will we need the full component of it?
No, there needs to be some angle.
Okay, so we need it twice, and we only need the x part, right? All right, so we need, if that's my angle theta, I want the cosine of theta, right? So cosine of theta equals, well, that angle is the same as that angle.
X over square root of x squared plus d squared.
Whoa, did you catch that? Because that little trick is going to reappear many times.
And c.
Okay, we don't have the actual numerical theta, so that's theta in what we know, or cosine of theta in what we know, right? So this right here becomes 2 times 1 over 4 pi epsilon naught q x squared plus d squared. And then I only want the x component
So
times
x over
x over square root of x squared plus d squared.
Wow.
Okay?
Cool.
Now let's combine that. First of all, does everybody see how that was arrived at? Now, dude, you could spend a half hour looking at that and pulling your hair out, right? If you had hair. Right? But it's not that bad, right? You got one component, you got two more components that are the same, so you double it, but you only want the x part of it. Right? That's it. Now, let's combine this to make it look a little bit nicer. I'm going to have 1 over 4 pi epsilon naught, and then I'm going to get a q over x squared plus this term over here. Okay, so I factored these two out.
You can even factor out the key.
I could factor out a q. I'm going to leave it in for just a second. So then over here, I end up with 2q x, thank you, 2qx over, okay, see these two?
Yeah.
This is to the 2 halves, and this is to the 1 half, right?
3 half.
So you get x squared plus d squared all to the 3 halves. And you're right, you could factor out the q. I should have done that. That would have been easier just to do it right here. So I'm going to factor out the q as well. So I put the q out here, and I have 1 there, and I got a 2x over there. And there's my answer.
Of course.
Now, we use symmetry. Now let's check at the limiting conditions to see what it looks like. Let's say that you march your little body down here and you stand right here. Okay? What kind of electric field would you expect to see right there?
Large.
Large from this one, and what would you get from these two?
Basically 0,
Not
because
that
it's
much.
mostly vertical.
Yeah, not that much. In comparison to this one, not much at all, but also it cancels itself out, right? Because this one and this one cancel each other out. So what you would expect to see would be an electric field that looks like this. 1 over 4 pi epsilon naught q over r squared. That's what you would expect to see.
Yeah.
Okay, now let's take a look at this.
Over x.
So if x goes towards 0, okay? If x goes towards 0, I want you to notice if this goes towards 0, then that goes towards 0. This term goes towards 0 because I have a number in the denominator and the numerator goes towards 0. So this disappears. And when that disappears, look what I get. I get,
Infinity.
well, this will go towards infinity, that's true, but this term becomes small compared to this term, right? So this term disappears, leaving me with
Yeah.
1 over 4 pi epsilon naught q over x squared. Which is what we'd expect, right? That looks good. Okay, if we're really far away, what would we expect to see? If we march our little bodies way out here,
Infinity.
what does it look like? It looks like a 3q, a plus 3q sitting out there, right?
Yeah.
All right, so let's look at that one. If x goes towards infinity, if we march our bodies way out there, if x goes towards infinity, or gets large, okay? If x gets large, do you notice that this term right here, d fails to make any difference anymore? And d kind of disappears. And when d disappears, look what happens.
X cubed.
You get x cubed. I get x over x cubed, which is the same as 1 over x squared here plus a 2 over x squared here, the same as 3 over x squared. And when you multiply that by this, what do you get? You get 1 over 4 pi epsilon naught 3q over x squared, which is what we'd expect to see, right?
Yes.
Sweet. That's pretty cool. So what we actually get is this. If we were to graph electric field versus radius, we'd have a line here and we'd have a line here. This is our 1 over 4 pi epsilon naught 3q over x squared, and this is our 1 over 4 pi epsilon naught 1q over x squared. And when we're close, which line do we match up with?
The left.
This one. And when we're far away, we match up with
That.
this one, right? So what we end up with is when we're really close, we're out here, and when we're really far away, we're out there. So that's what our graph would look like. It would transition from one to the other. Okay? All right.
It's a weird way of thinking. 'Cause I was just
Ooh,
Whoa.
thinking zero.
message from the Great Wall.
Of course.
You're gonna get paycheck.
So, Mr. Bruin,
Yes.
on that top graph, that should go to zero, right?
And eventually, when we go way out, this will go towards zero. That's correct. This will eventually go towards zero. That's correct.
Taper out.
Because that's how I think of it, like not the, which graph does it approximate?
Well, yeah, it starts here, but then it migrates towards this one. So it approaches zero at the rate of this one, not at the rate of this one.
Yeah, that's just
Funky, funky.
it's fresh.
All right, let's do our next one. Okay, let's talk about a dipole.
Let's.
All right, a dipole. A dipole is two opposite charges, equal and opposite charges, separated by a distance. So if you have a plus charge and a minus charge, and they're separated by a certain distance, d, okay? The two charges are the same. So the net charge equals 0, but the thing has an electric field. Okay? Weird. So it has an electric field that actually looks like this, right? Which we already know.
Sounds earthy.
But when you get very far away, it disappears, right? Okay? So its net charge is 0, yet it has an electric field. Now there are induced dipoles, like when you have a charged object, like when a big thunderstorm cloud comes over the Earth, it induces a dipole in the Earth, it induces a mirror charge in the Earth, plus and minus, or minus and plus, I don't remember which one it is.
And a bolt
Okay.
light.
Yeah, then a bolt of lightning hits. Or you could have a like a permanent one, like this one.
Mickey Mouse.
There you go.
Or water.
Or water. Water is a permanent dipole. Okay? Polar molecule. All right. Now, a couple things about this thing. This thing will have an electric field that you can calculate. So like for instance, if you have a plus charge here and a minus charge here, you ought to be able to calculate the electric field here and here. Okay? At point A and point B. Okay? Now, thinking about it, at point A, which way will the electric field point?
It
Up.
can.
Because this one's positive and that one's negative, the plus is closer, so it'll be up.
Well, unless, right? If the negative's really big.
It's a dipole, so they're the same charge.
Net charge is zero.
Oh.
The electric field is up because it's a dipole. The two charges are the same. Okay, which way is the electric field here? Where that's my positive and that's my negative.
Silence.
Sort of like this way.
It should be down.
Draw the
It should
arrows
be
and then
down, right?
Okay, what way is the electric field because of this one?
away. Away.
I'm just looking at the
Zoids and away.
one on the left.
Which way is this one?
Back.
Toward. And they're exactly the same, right?
So it's
Due to
down.
symmetry, which way is it?
Down.
Okay, when you add these two up, it'll be down. The electric field is down
Do we
here.
have to draw the other one? The other one?
Other one for the other one.
The negative doesn't affect it at all?
This one?
Yeah.
It does. What we end up here is we end up with
Like a
a
little.
with a positive one and a negative one. And the
Ah,
negative
okay.
one is smaller because it's farther away. So you end up with it pointing in the positive direction. But it will be smaller than the electric field just due to that. Okay? Good question. All right? By the way, a dipole. What will a dipole do in an electric field?
Spin.
So like if I take Mickey Mouse and put Mickey Mouse in an electric field that is this way.
Well, except the e-commerce not do that.
Okay.
anymore, so that's not true.
What will it do?
I think
Consider it as like a whole thing, so as a net charge of 0.
As a net charge of 0. So will it move? Wait a minute. Think of,
Oh, it won't
will
translate.
it translate?
No.
No, but it will probably
Will it rotate?
spin.
Yes.
Okay.
I was right.
It has no net charge, so therefore it will not propagate through the field. How I know? Well, you could. All right, but which way will the pluses receive a force?
To the right.
To the right. Which way will the negative experience a force? To the left. So what will Mickey do? Mickey will torque and rotate and spin, but will he spin like this?
Center mass.
It'll spin one way.
He will spin, whoa, 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 back and forth. Because when Mickey gets here, then the forces are like this and like this. He's in equilibrium.
So.
But there's no friction, so he'll oscillate through that position
Yeah.
to this position. And then the forces are this way. And so he'll oscillate this way, through, and then back. So I won't oscillate up and down, but we'll oscillate.
It's never
Is there any way to put it in rotational equilibrium?
Well, if there's friction, what'll happen is that they'll oscillate. They'll either oscillate just to that one spot if there's a lot of friction. If there's a little friction, they'll oscillate back and forth, but end up damping out to that one position. You can actually, so like for instance, if you take a charged object and hold it next to water, the water molecules will whoop, and they'll rotate because there are other water molecules that they rub against. That they will end up rotating
So
and
if
aligning.
If I had a death wish, would I see anything? If I like put a charged object in one?
No. Here, go home, get a balloon, rub it on your cat, okay, and then have a stream of water. Have a stream of water coming down from the faucet. It helps if it's a little stream because it has less mass than. Hold the balloon close to the water, and the water will be attracted to it
That's exciting.
because it's rotating and attracting. Now, yes, very nice.
If I stripped a wire and ran, plugged it in a wall,
Would it like if you stripped a wire, covered yourself in
Yeah.
cooking oil, ran through the streets during a lightning storm?
yeah.
Is that where you're going with that, right?
You'll be really tan.
You'll be tan. You won't need to shave for months. Okay, now it's time for us to progress to the fun
Just
stuff.
shaves enough.
Yes.
I'll pretend I didn't hear that. Okay, everybody, it is very common. It's very common on the test to have like a plus charge, a minus charge, and a plus charge on the exam. They'll ask you, what's the electric field here? What's the electric field here? Okay? Or they'll have like a plus charge, a minus charge, and a plus charge. And they'll ask you, what's the electric field right here? And keep an eye out for symmetry, okay? They could have something like a plus charge and a plus charge and a minus charge if they wanted to be rude and find out the electric field is there at the corner of a square or something. All right? So they could do that. Or they could have a plus charge, and a minus charge and find it at the center of your equilateral triangle. That's probably one of the harder ones you have because of the geometry and finding the radius and everything, right? But it could be done. All right, that's the one we did. Okay? So all those things are very likely, and it might be symbolic. Okay? It might just be symbolic. All right. Now, But that's all stuff we could have done back in Physics B. So let's move on.
In 2 minutes?
Yes.
Okay. It is 5 minutes. I need to fix my watch.
I think
Okay,
Tom's-
continuous distribution of charge. Hope I spelled that right. All right, it's impossible to keep track of individual charges. All right, because the charges are so small, there are so many of them, like in a wire or in a capacitor and things like that. So, there are a couple of reasons why we need to do this. One is for practicality. The other is because it's going to help us out, and you'll see why in a minute. But we have to know this thing called charge distributions. This. Thank you. My spelling is in hiatus forever. All right, so here we go. We have volume, area, and linear, otherwise known as 1D, 2D, and 3-dimensional densities. Okay, this is the density you're used to, is volume density. Used to mass over volume, but we're not talking about mass right now. We're talking about charge. So our volume distribution of charge, instead of being mass over volume, will be Q over V.
Is that right?
Is that the same?
Actually, let me put capital Q so this is the, okay? That's the same rho, by the way, as mass density. We're going to recycle rho for volume density for charge distributions, okay? All right, for an area charge distribution, we'll use the symbol sigma, and it will be charge, the total charge, divided by the area instead. And for a linear one-dimensional charge distribution, it will be lambda.
So
Lambda will be charge over length.
that's what we did with mass. right?
Now we've done this also with mass. Now, like for instance,
Symbols.
if you, yeah, even the symbols are the same as for mass distributions, densities. All right. So, like for instance, when they measure the mass of wire, it's easier for them to figure out the mass per unit length of wire. Okay. And if they have like a flat sheet of metal, it's easier for them to figure out the area density, mass per unit area. We're going to do charge per area, charge per length, and charge per volume. Okay? Now, quick note. All right? Looky.
Is that DQ?
What's this D business? Stop it, you're killing me. All right, if you want to find out, if you're doing integration, why would we do integration? All right,
To equal to that? Or take it in 5?
yeah, a small amount of volume will have a small amount of charge in it, right? A small amount of area will have a small amount of charge in it. A small amount of length will have a small amount of charge in it. So dq over dl will also give you the same density. dA, or dq over dA, dq over dV give you your sigma, your area, and your volume densities. Okay? All right, here you go. When we solve these things with continuous charge distributions, here's rule number 1. First thing you look for is symmetry. Do we have any symmetries that we can use? Rule number 2. Assume a small dq
That's what I like about it.
point of charge, or point charges. Assume small dq point charges. So dq, we're looking for little dqs, not Dairy Queens. All right. From this little dq, we'll calculate a little electric field, a little dE.
Wait, what? Say that again?
So like for instance, if I have a line of charge like this, and I want to find the electric field right there. Okay? First of all, I'm going to look to see if there's any symmetries. If there is or not. Next thing, I'm going to pick a little DQ. There you go. There's my little DQ. DQ.
From a little.
My little cute little DQ will produce a little cute DE.